Well, welcome back. Thanks for coming again to watch another exciting episode of Something About Chemistry. Oh, yeah, we've been talking about how fast reactions go and the factors that affect, the factors we can measure and predict how a reaction will proceed and describe how it progresses over time. We may have mentioned this in our study of rates, reaction rates, but we haven't yet in simply writing rate laws, we haven't addressed the temperature issue. Excuse me. Of course, we all know, don't we? Do we? I don't know if we all know this is common sense or not, that most warm reactions go faster than most cold reactions. Not always true, but the vast majority of reactions go faster when they're warmer, and that probably has to do with collisions, like how frequently the particles collide with each other. Part of another video called perhaps collision theory and collision theory, and I forget what else. Okay. Oh, mental blank. Oh, transition states and collision theory. In any case, here's a famous equation. Uh, it's only about 100 and some years old. This gentleman is credited with coming up with it, although I don't think I'll have used it very often in this form. Because, as I say here, coming up with a term for A is difficult. As particles collide, they need to collide with the proper orientation and the correct amount of energy. That determines what A, capital A, is. Well, then it's measurable, but rarely predictable. This is an exponential, e to the negative activation energy divided by the gas constant in energy units and the Kelvin temperature. So that's too complicated. Let me simplify it a little bit. There's him, Svante Arrhenius, very famous guy. So we know that most reactions go faster when they get warmer. Let's manipulate this a little bit. The A term is a little bit deceptive or devious or elusive, I should say. The activation energy is, of course, the energy it takes to get the reactants up over the activation energy barrier and create the products. Previous to this equation, this idea, we had really no way of knowing or to calculate what the activation energy might be for a given reaction. R is just the gas constant in energy units, and T is the Kelvin temperature. Kelvin, absolute temperature scale. Let's manipulate further. On this one, we take the natural logarithm of both sides. If you're good with math, this makes totally good sense. If not, you may be a little bit scratching your head about how do you do this. Take the natural logarithm of both sides. That gets rid of the exponential and just gives you EA over RT. There's a negative sign thrown in there. But still, since the A is not always easily obtainable, let's take what we call a two-point form of the Arrhenius equation. If I compare point 1 with temperature 1 and constant 1, rate constant, this is the rate constant in the rate law that we've always been looking at previous to this. And isn't it true then that most warm reactions go faster than cold reactions because the particles are vibrating, moving about more quickly, collide more frequently. More frequent collisions result in a faster rate, and a faster rate could be reflected by a larger rate constant. So K1 and T1 and K2 and T2. If T2 were warmer, then I would predict K2 to be larger. Let's compare those two in a ratio, and we get something like this. Although that's not super convenient either. There's a property of natural logarithms or base 10 logarithms. When you subtract them, you end up dividing both sides. Taking K2 over K1. It's a good thing I'm not your math professor. That's sloppy. In any case, this is a couple of ways you'll see it. K2 over K1, natural logarithm. Reciprocal of T1, temperature, Kelvin temperature, Kelvin temperature, T2. Sometimes you'll see a negative right here, but if that's true, then these T1 and T2s will be reversed. It'll be T1 minus T2, or reciprocal of T2 minus reciprocal of T1. I won't expect you to memorize this equation. We'll give it to you on the exam. Let's go to practice with it, though. Let's look at a couple of examples of how this is used. What if I had the same reaction, I should say, going at two different temperatures, 20 degrees Celsius and 30 degrees Celsius? Well, first of all, I can't use Celsius, correct? I must use the absolute Kelvin scale. The activation energy is described to us as 50 kilojoules per mole. So really, this is kind of a plug and chug question. I put 50 kilojoules here, the gas constant R in energy units here, the Kelvin temperature 2, Kelvin temperature 1. Honestly, I don't always write it out this way. I usually write it out the other way. It depends what form of the equation, what 2-point form of the equation I'm given or what I'm able to look up. Interestingly, solving for the math, again, the reverse of the natural logarithm is the exponential. The reverse of the exponential is the natural logarithm. So they're integrally connected. To get rid of the natural logarithm, I take e to the x on this side, e to the x on this side. It comes out to about 2. What does that mean? That means for 30 degree Celsius reaction versus a 20 degree Celsius reaction, only 10 degrees warmer, my rate of the reaction is about twice as fast. K2 compared to K1 as a measure of the rate of the reaction, about 2 times faster for 50 kilojoules per mole. Of course, that could change, but that's a very representative figure for a lot of reactions in that ballpark anyway. Maybe we'll come back and look at that one like that again, I think at the very end. This is a little bit blurry, but I just snipped it off the internet. Different ways to write the Arrhenius equation. You'll probably see this last one, although that negative could be eliminated if I put 1 over T1 minus 1 over T2. Just take that negative into the parentheses. Again, don't remember that. Don't remember the equation. Don't memorize the equation, but do practice with it enough that you can do it. Here is a memorable take-home message, though. I would like you to memorize this. If I were to graph the relationship between the Kelvin temperature and the rate constant, little k, in order to linearize the data to make a mathematical trick be productive and useful, I take the natural logarithm of my rate constants and the reciprocal Kelvin temperature that goes with those. So I might have a point here and 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 a point here. We find that those are it's a linear relationship. If you have a hard time imagining this, I'm sure there's some questions in the back of the chapter that give you some data and say, manipulate this. Take the Kelvin temperature, take the reciprocal, take the natural logarithm of the rate constant little k, make a graph, find the slope. What does it mean? Struggle with it. If you don't take the time to struggle with it, it's a little bit mysterious. But you'll notice this is in the form of y equals mx plus b, the famous slope-intercept form of in math, the slope-intercept form of an equation of a straight line. So again, that's the y-axis, there's the x-axis, there's the slope of the line, and there's the intercept, the y-intercept. The key point here is the slope of this line. If I were to graph this data in this way, the slope of the line can tell me what the activation energy is. I've seen those types of questions frequently, hint, hint, wink, wink, on tests. So if I do such a thing, sorry this is kind of sloppy, I wrote in hand over a pre-printed slide I had found. If I take the natural logarithm of the rate constant versus the reciprocal of the Kelvin temperature, and if I know the slope, in this case the slope it's almost always negative tending in the negative direction. So the negative of the slope equals the negative of the activation energy over the gas constant. And the gas constant, you don't have to memorize that either, but it's always given to you. But just solve for the activation energy. And this is in joules, this is in joules, I think it is. Okay, oh yeah, that's joules per mole. Kelvin, the slope, oh that's a bit messed up, but I think it all works out. Comes out to 93,000 kilojoules for this activation energy. That's a little bit larger of an activation energy than the last example we saw like this, but still. And just to reiterate, very, very common form of the Arrhenius equation. Don't memorize it, it's given to you. Here's another one. Let's see, I have a rate constant of 2.5-ish at a 701 Kelvin. What if I warm the temperature up to 895 Kelvin? Well, I predict that the rate constant will go, oh my goodness, it went from 2.57 1 over molarity seconds to 567 1 over molarity seconds. So from that I'm supposed to find out the activation energy. So here's K2, and that goes with T2. So, no. Well, it doesn't matter which one I call K1 and K2. I call this K2, so if that's K2, it goes with 701. So if this is K2, 2.57, it goes with T2 right here, and that's 701. Take the reciprocal. Sometimes, remember, they'll give you the Celsius, see if they can trick you up. But remember, you have to use Kelvin. And so pluggish and chuggish, so this answer divided by 8.31 is a small number, 0.000372. This comes out to negative, and this, I don't know. I may have thrown a negative in there randomly, willy-nilly. Can you do that? In science we do sometimes. It's a little mistake here somewhere. I'm not comfortable with it, but let me ask you this. Can energy be negative? Yeah, it can, but what does it mean? Energy negative means it's exothermic. I think this is endothermic because activation energy is the energy you need to put into a reaction to get it going. So probably that's why I pulled the negative out of my hat and just stuck it in there for convenience. If I didn't, this would be a negative 145. An activation of energy of negative 145 kilojoules doesn't mean a lot because it's negative energy or negative energy change is an exothermic or exoergic process, which means the energy is given off. And that doesn't make much sense. So anyways, here's another example. If you want to pause the video and work it out, looks like I'm given an activation energy, I'm given constant 1 and a temperature of 25 degrees. I'm given a warmer temperature of 45 degrees and asked to solve for the second constant K2. Jeopardy music, pause the video if you'd like, or here's the answer. So I don't know my second constant, which goes with the warmer temperature. Right here, the warmer temperature. The cooler temperature has this constant. The activation energy in kilojoules per mole. This is in joules per mole. Change one of them. You could change this one to kilojoules or this one to joules, whichever, just make them match up. I solved out to be 0.25. Does that make any sense? 0.25. So if I warm a reaction from 25 to 45 Celsius, the constant K1 should get larger from 0.087 to 0.25. Yeah, that makes sense to me. It's about right, I guess. And lastly, this is kind of a silly reiteration of that 10 degrees Celsius rule of thumb. If I warm a reaction up 10 degrees Celsius and my rate constant changes, that means the rate goes about twice as fast. It is often said that the rate of reaction doubles, gets times by 2 for every 10 degrees Celsius. So my constant 2 would need to be 2 times larger than constant 1 to make my rate 2 times larger. Think about the rate laws. Rate equals little k times concentrations, but here we're talking about temperature. So, in any case, the natural log of 2 is 0.693, and the difference in my Kelvin temperatures, the difference in the reciprocal of my Kelvin temperatures, solve for activation energy. In the question previous, we had 50 kilojoules per mole. This one solved out to be more exactly 53.6 kilojoules per mole. But in any case, that might give you some kind of an idea about how to use this silly equation. But I'm sure you'll see it again. Thanks for watching, guys. See you in class.